So, let's go. Number 1. The leopard spots. You are standing in a dry riverbed on Mars, and the most important rock in human history is under your boots, and you cannot see what makes it important. It is called Chayava Falls, a flat slab of reddish mudstone in a dead channel that once carried water into a crater called Jezero. In July of 2024, a rover named Perseverance pressed a drill into it and pulled out a finger-length core. Then the scientists looked at what the drill had exposed, and the room went very quiet. The rock is covered in spots, pale in the middle, dark around the rim, scattered across the surface like the markings on a leopard. Each one is about the size of a peppercorn. And inside those spots, the rover found a specific pair of minerals tangled up with organic carbon. One is an iron phosphate called vivianite. The other is an iron sulfide called greigite. Here's why that made a room full of careful people stop breathing. On Earth, those two minerals form together in one very particular situation. When microbes eat organic matter in wet, oxygen-poor mud, they leave those exact chemical fingerprints behind. Bogs do it. Buried bones? Do it. There are even bacteria that build tiny chains of greigite crystals inside their own bodies to steer by magnetic fields. Living things, doing what living things do, make this pattern. And the spots are not just sitting there. They mark a boundary, a place where two kinds of chemistry meet and react, and that reaction releases energy. The exact kind of energy a hungry microbe would love to sit on top of and feed from. In September of 2025, NASA said the words out loud: potential biosignature, not we found life. Something more careful and somehow more haunting. A feature that could be the trace of something once alive, sitting in a rock, waiting for someone to prove it either way. Because here is the catch, and it is a real one. Plain chemistry, with no life involved at all, can make those same spots. Cold water, iron, a little sulfur, and enough time, and you get leopard spots with nobody home. So this is where you start. Not with maybe out at the edge of the galaxy, with a rock you could hold in one hand, marked with a pattern that on your home planet almost always means something was living there. And this is only the first thing Mars has handed us. Number 2, something could be alive. Down there right now. Everything about Mars trains you to think in the past tense. Ancient rivers, old lakes, a world that had its chance billions of years ago and blew it. But in 2024, a study did something that should genuinely unsettle you. It moved the question into the present. Picture the ice on Mars. Not clean, glassy ice. Dusty ice, full of fine grit blown in over ages. And that dust turns out to matter enormously. If you go down into that dusty ice, something strange happens to the light. The ice lets enough sunlight through to run photosynthesis, the same reaction that feeds almost everything alive on Earth. But that same layer of ice overhead blocks the radiation that would fry anything living. Above you, lethal ultraviolet. A few centimeters down, filtered, gentle light. And in between, if the conditions are right, a thin film of liquid water that the ice keeps from boiling away into the thin Martian air. The dust is doing something clever here, and it is a real balancing act. Too much dust, and the light never gets through, and it is dark all the way down. Too little dust, and the radiation punches straight through and sterilizes everything. But there is a sweet spot, a just right amount of grit, where a cell sitting a hand's depth under the surface gets light to eat by and a roof thick enough to survive under. Scientists gave this a name. A radiatively habitable zone, a place where light and water and shelter all overlap. In dusty ice, it could sit as shallow as 5 centimeters down. In cleaner ice, as deep as 3 meters, roughly the deep end of a swimming pool, except the pool is frozen and buried on another planet. And it is not some exotic corner of Mars. The best spots are the mid-latitudes, the same broad bands where Earth keeps most of its cities. Sit with what that means. This is not a story about what Mars used to be. This is a real physical, present-day place where a living cell could, in principle, be getting light and water at this exact moment while you listen to this. Nobody has dug down and found a cell there. Not yet. But for the first time, the honest answer to could something be alive on Mars right now, stopped being no. It became, we should probably go look. Number 3, the cracks that build life. Water is not enough. This is the thing people miss. A puddle that sits there, calm and stable, is actually a bad place to build life. What you want is a puddle that keeps drying up. On Mars, Curiosity found exactly that. A patch of ancient mud, cracked into a honeycomb of hexagons, the cracks meeting each other in neat little Y-shaped junctions. If you have ever seen a dried-up lakebed on Earth, you already know this pattern. But the shape is the whole story. A single flood dries once and cracks in long straight lines. Hexagons are different. Hexagons only form when the mud dries, gets wet again, dries again, over and over, on a steady rhythm. This mud was not a one-time puddle, it was cycling, wet, dry, maybe with the seasons, for a very long time. The rock even sits right at the boundary between a clay-rich layer below and a salty, sulfate-rich layer above, exactly where you would expect water to keep coming and going. And that rhythm is not a boring detail. It might be the single most important thing on this whole list. Here is why. When chemists in a lab try to build the long, complicated molecules that life needs, the chains that become DNA and proteins, they do not just leave stuff sitting in water. Water alone tends to pull those molecules apart. So what do they do instead? They wet the mixture and dry it, then wet it and dry it again. Each time it dries, the molecules get crammed together and forced to bond. Each time it wets, they loosen and rearrange. Do that enough times, and simple ingredients ratchet up into the long chains life is made of. That is exactly what these cracks are recording. Mars was not just holding water, Mars was running the machine. The same wet-dry cycle we use on Earth to coax life's chemistry out of plain chemicals was happening on its own, out in the open, on a regular beat, for ages. It is one thing to learn that Mars was wet. It is another to learn it was wet in precisely the way that assembles the molecules of life over and over without anyone setting it up. Which raises a very uncomfortable question. If you build the experiment and you run it long enough, what exactly do you expect to happen? Number 4, the spiderweb underground. You keep hearing that Mars dried out, rivers gone, lakes gone, the surface turned into the cold desert we see today. And that is true. But it hides something. And Curiosity just drove straight into the proof. High up on the slopes of a mountain inside Gale Crater, the rover reached a landscape that looks like a spiderweb made of stone. Low ridges of hard mineral crossing and recrossing each other into a giant honeycomb lattice. From orbit, it stretches for kilometers. Geologists call it boxwork. Here's how you build a thing like that. Long after the surface lakes were gone, water was still moving underground, trickling through cracks in the buried rock. As it moved, it dumped minerals into every fracture, filling them, hardening them into something like natural cement. Then, over ages, the Martian wind sandblasted the softer rock away and left the cemented cracks standing up like ribs. What you're looking at is a fossil of where groundwater used to flow. On Earth, you mostly find boxwork tucked away inside caves where a ceiling protected it. On Mars, it is right out in the open because there was no cave. The wind itself did the digging, stripping away everything except the hard mineral veins, and groundwater changes the whole timeline. When the surface freezes and the rivers vanish, life on the surface is finished, but underground, shielded, wet, and a little warmer, a habitable pocket can keep going long after the world above it has died. When NASA studied these ridges, they concluded the ancient water table sat higher and lasted longer than anyone had thought. The livable zone was not a thin skin on the surface, it ran deep and it ran late. So the surface drying out was not the end of the story, it was just the part you can see from space. Below it, in the dark, water kept flowing through the rock, keeping a niche open, in exactly the kind of sheltered spot a microbe could hide. And the team is not done. They are now hunting through those stone ribs for organic molecules, the chemical leftovers of life, sealed into the cement where groundwater once ran. Which brings up the obvious question of what exactly they are hoping is preserved in there. Number 5. The missing ingredient was there all along. Run down the shopping list for life and you get to nitrogen fast. Your DNA needs it. Your RNA needs it. Every protein in your body is built around it. No nitrogen, no life as we know it. Full stop. And for a long time, Mars looked like it failed this test. There is nitrogen gas in the thin Martian air, but that form is basically useless. The two atoms are bonded together so tightly that living things cannot pry them apart without help. It is like having money in an account you can see but never withdraw. Then Curiosity scooped up some Martian soil, heated it, and watched what came off. And there it was. Nitrogen, but in the useful form. Nitrates. The kind of nitrogen that life can actually grab and build with. It turned up in the wind-blown sand, and in the old mudstones of a spot called Yellowknife Bay, at concentrations reaching around 1100 parts per million. That is thin, but it is real, and it is spread around in more than one place. Ancient Mars was not nitrogen-starved after all. It had a usable supply sitting right there in the ground. Where did it come from? Almost certainly not from life. The best guess is brute force. Meteorite impacts and lightning, both of which can slam that stubborn nitrogen gas apart and lock it into nitrates. Violent, mindless, and exactly what a young, chaotic world had plenty of. But that does not make it less important. It makes it more. Because it means Mars could have run a nitrogen cycle, the same kind of loop that keeps life fed on Earth, without ever needing a living thing to start it. The account was not just full, it was unlocked. So tally it up. Water, check. Wet-dry cycling, check. And now the nitrogen problem, the one that should have stopped Martian life before it began, solved by nothing more exotic than lightning striking an ancient sky. The pattern is getting hard to ignore. Every time we look for a reason life could not have happened here, Mars quietly hands us the missing piece. Number 6. The water that wouldn't leave. Everyone loves a clean story. Mars was warm and wet, then it froze and the water left. Simple. But Curiosity found something that smears that clean line into a much stranger shape. Cutting across the rock in Gale Crater are pale streaks, halos running along old fractures, lighter than the stone around them. When the rover checked what they were made of, the answer was opal, the same water-rich mineral you might know from a ring. And this Martian opal is holding a real amount of water locked inside it, several percent by weight, just sitting in the rock, ready to be released. Here's the part that matters. Opal like this forms when water dissolves silica and then leaves it behind in the cracks. A bit like the ring left, when water evaporates from a glass. And these halos are young. They formed from water moving through the rock long after the surface had already gone cold and dry. This is not a leftover from the warm and wet golden age. This is water showing up late, running through the fractures after the party was supposedly over. And underground, along those cracks, is a genuinely good place to be alive. You are shielded from radiation by the rock above you. You have liquid water. You are tucked away from the brutal, freezing, blasted surface. In a lot of ways, it is more habitable down in those fractures than anywhere up top. So the window for life on Mars did not slam shut when the lakes dried. It stayed cracked open, in the dark, in the rock, for far longer than the neat story allows. Every one of these pale halos is a little handwritten note that says the water was still here, still moving, still doing the one thing life absolutely requires, long after Mars was supposed to be a corpse. Mars, it turns out, is very bad at letting go of its water. And that is exactly the problem for anyone who wants to believe this planet was always dead. Number 7. Organics everywhere, not just one rock. When you hear that a rover found organic molecules on Mars, it is easy to picture one lucky rock, a single freak sample that happened to have some carbon in it. Interesting, but maybe a fluke. Here is where that comfort falls apart. Over in Jezero Crater, Perseverance carries an instrument named Sherlock, built to hunt for exactly this kind of chemistry by shining ultraviolet light at rocks and reading the glow that comes back. It looked at 10 different targets across the crater floor. And it found signals of organic molecules in all 10. Not one rock. Every rock it seriously checked. In 2 different geological formations bound up with minerals like sulfates and salts spread right across the landscape. And these are not fresh. The molecules have been sitting there, preserved in the stone, for somewhere between 2.5 and 2.6 billion years, older than complex life on Earth, waiting quietly in Martian rock the entire time. Now, careful is careful, so here is the honest caveat. Some of those glowing signals could, in principle, come from certain minerals rather than true organics, and scientists are still arguing the fine edges of it. But the broader picture holds, and the confirmed detections are real. The building block chemistry of life is not a rare accident on Mars. It is common. It is durable. It is basically everywhere the rover points. And think about what organic even means. Here. These are carbon molecules, the exact family of chemistry that every living thing you have ever met is built from. Mars had them in bulk, in multiple places, delivered possibly by water, or volcanoes, or falling out of the sky, and then locked safely in rock for billions of years. So the raw material was not scarce. The ingredients were stocked planet-wide and preserved. Which leaves a very pointed question hanging in the thin Martian air. If you have the ingredients, and the water, and the shelter, what is actually stopping the reaction? Number 8. The reagent that makes RNA possible. There's a problem at the very beginning of life, and for a long time it drove scientists a little crazy. To get life started, most theories say you first need RNA, a molecule a bit like DNA's older, simpler cousin. And to build RNA, you need a sugar called ribose. And ribose has one very annoying habit: left alone in water, it falls apart fast. It just will not hold still long enough to become anything useful. For decades, this was a genuine roadblock. How do you build life's first information molecule out of an ingredient that keeps self-destructing before you can use it? There's one clean fix chemists know about: boron. When boron dissolves in water, it becomes borate, and borate grabs onto ribose and stabilizes it. It holds the sugar together long enough for the next step to happen. Boron is like a hand steadying a wobbling tower, just long enough for you to place the next block. So when Curiosity found boron on Mars, that got attention fast. Its laser-firing instrument spotted it inside mineral veins in Gale Crater at hundreds of parts per million, and the location tells you something crucial. Boron in those veins means boron was dissolved in the ancient groundwater, and the chemistry of where it settled tells you what that water was like. Mild. Not boiling, not acid. Somewhere in the range between freezing and a warm bath, neutral to slightly alkaline. The kind of water you could actually put your hand in. Now line it all up. Mars had liquid water you could survive in. It had carbon, the backbone of life. It had usable nitrogen. And now it turns out it also had the one weird specific ingredient that fixes life's most fragile first step. In rock about 3.8 billion years old, right in the same window when life was first stirring back on Earth. At some point, the list stops sounding like a coincidence and starts sounding like a recipe someone left out on the counter. Number 9. A battery with no sun required. You can have all the ingredients in the world and still get nowhere, because life does not just need parts. Life needs power. Something has to feed the reaction, keep it running, keep it building. And this is where people assume Mars finally runs out of luck because it is cold and dim and a long way from the sun. Except Curiosity found the power supply too. Back at that ancient lake in Gale Crater, the rover read the chemistry of the old lake bed, and what it described was a genuinely comfortable place to live. The water was neutral, not acid. It was not too salty. And crucially, it held iron and sulfur sitting in a mix of different chemical states. That mix is not just trivia. That mix is food. On Earth, there are living things that never once see the sun. Down at the bottom of the ocean, deep inside solid rock, they survive it by eating chemistry. They pull energy straight out of iron and sulfur, out of the simple difference between one chemical state and another. No sunlight required at all. We call it eating rock, more or less, and entire ecosystems run on nothing else. Gale Crater had exactly that setup. Where the surface water mixed with groundwater, the energy you could get from just oxidizing iron works out to be roughly the same as what real iron-eating microbes live on right here on Earth today. Not a faint trickle. A usable, steady, life-supporting current. And when scientists tallied up the elements in that old lake, they found the entire set. Carbon, hydrogen, oxygen, sulfur, nitrogen, phosphorus. Every single element life is built from, all measured, all present, all in one habitable place. So add it up honestly. Mars had the water, it had the building blocks, it had the shelter, and it had a battery, a real energy source a microbe could plug into without ever seeing daylight. Everything on the checklist for a living world, checked off one by one by a robot the size of a car. Which leaves exactly one question worth asking, and it is the hardest one of all. Number 10. The answer is in a tube, and it's stuck. Here is what should be the triumphant ending. That rock from the very start, the one covered in leopard spots, the potential biosignature, the clearest hint of ancient life we have ever found. We did not just photograph it and drive away. Perseverance drilled a core of it, sealed that core inside a pristine titanium tube, and set it carefully aside. Its name is Sapphire Canyon. By the middle of 2025, the rover had filled around 33 of these tubes. Rock cores, soil, even a sample of the Martian air. The most carefully chosen collection from another world ever assembled, sitting on the surface of Mars, sealed, labeled, and ready to travel. And there is a hard reason it has to come home. From orbit and from a rover, we can find a potential biosignature, but we cannot finish the argument. Was it microbes, or was it just chemistry? To settle that, you need the giant, delicate instruments that only exist in laboratories on Earth. You need to physically bring the rock here and take it apart. The tube is not the answer. The tube is the question, sealed up, waiting for a lab that can crack it open. And here is the turn. The part that should make you a little angry. The evidence is ready, the rock is drilled, sealed, and sitting right there. The hard science of how to go get it has largely been worked out. What is missing is not distance, and it is not physics. What is missing is us. In January of 2026, the program built to bring these samples back to Earth was defunded. The budget was zeroed out. Right now, as these tubes sit in the Martian dust, there is no approved, funded mission coming to retrieve them. Think about that for a second. The single best chance to answer whether we have ever been alone, one of the oldest questions our species has ever asked, may already be solved. The evidence may already be collected. It is just parked on another planet in a sealed metal tube with no ride home. The proof of whether Mars was ever alive might already be lying in the red dust, sealed and waiting, and for now, nobody is coming to get it.